So we are moving on here in Unit 3. We talked the last couple of days about angles, so I want to do a little bit of a review. There's a quiz out there in Blackboard. I believe it's labeled quiz 47, 48, 44, 45, sorry. Ahead of myself. 44 and 45, and what that means is that 44 and 45 stands for the sections of that packet we've been doing homework out of. Sections 44 and sections 45. So the things I want to remind us of are operations with angles. We have two angles, share a vertex and share a side. Those are what are referred to as adjacent. And adjacent angles are additive. So that means I know this angle here is 71 degrees. And this angle here, 109 degrees. The whole angle here is found by just adding them together. 71 plus 109. 108 degrees. Now, of course, this is another special relationship when we have two angles that add up to 180 degrees. They are called, do I remember the word? Complementary. What if we have angles that are obviously supplementary? One of the angles is given 112 degrees, 41 minutes, seconds. I want to find the other angle. Oh, it's going to be found. Supplementary means they add up to 180. If I say it's 180, I have to write it as 180 degrees, 0 minutes, 0 seconds. Subtract 112 degrees, 41 minutes each. 0 minus 18 can't be done, so what do I have to do? I have to borrow, exactly. There's nothing to borrow from here, so we do go all the way to the 180. That becomes 179. That 1 degree that we borrowed would make this 60 minutes. Now, of course, we need to get it down here, so we're going to borrow from that and make it 59 minutes. Now we can subtract. 60 minus 18. 59 minus 41. And 179 minus 112. So we get the supplement, 7 degrees, 18 minutes. We have two adjacent angles that add up to 90 degrees. Let's say I know that this angle here is 28 degrees. I can find this one up here by simply doing 90 minus 28. That's 62 degrees. Two angles that add up to 90 degrees are called what? Complementary. Good. I can have complementary angles, again, that have a little bit uglier. And let's say I know that this angle up here is 71 degree, 18 minutes, 27 seconds. How would I find this angle down here? 90 degrees, 0 minutes, 0 seconds, minus 71, 18, 27. And again, we go to subtract. We can't do 0 minus 27. We have to borrow. There's nothing here to borrow from. Borrow from the 90. That's 89 degrees. We've borrowed 1 degree, which makes this 60 minutes. Didn't over here yet, so we're going to borrow from the 60 to make it 59. It's now 60 seconds. Now we can subtract. What is 60 minus 27? 33 seconds. 59 minus 18? 41 minutes. And 89 minus 71? 1 minute, 33 seconds. Looked a little bit at measuring angles yesterday. So first of all, looking at that at an angle there, is it obtuse or acute? Obtuse. It's bigger than 90 degrees. So when we look at our protractor, we're going to have to take the angle measurements that are bigger than 90. Because there will be 2 sets of them there. This will be labeled 140 degrees and 40 degrees. And these aren't way blown out of proportion. That one would be labeled 150 and 30. Of course, we want the larger numbers because this is an obtuse angle. So we're dealing with the 40 and the 150. I didn't draw those anywhere near to scale, but this would be measuring what there? 145. Standard protractor isn't too bad to read. You just have to be careful to make sure you count the lines right. It's that bevel protractor that we need to be careful with. So let's say this is the main scale of our bevel protractor. And on the vernier scale, 0, now, first of all, where do we read the main scale in this one? Read the main scale. 0 of the vernier scale is. What does that read here? Between 58 and 59, right? So we read the 58 degrees. The smaller one is what we want. Now the vernier scale goes both directions. Do we go to the left or do we go to the right to read the vernier scale here? We're going to go to the left. How do we know that we have to go to the left to read the vernier scale in this one? Yeah, the main scale is increasing going to the left. So we read the vernier scale always in the direction in which the main scale is increasing. We have to go to the left. Now we find the first line then going to the left that lines up. Not the 5, 10, 15, 20, 25. 5 looks like it's lining up. So that is 58 degrees, 35 minutes. That's really as precise as we can get with most of our common, unless we have a laser measurement system. That's really as precise as we can get. And we've seen an optical comparator, you can get a little bit more Pretty tough. I don't think we even have one of those here anymore. Have one. I used to actually have my own hardness tester and stuff for material science class for you guys. When they shut that down, I think they got rid of. I know they got rid of my hardness tester, and I think they got rid of the optical comparator as well. Okay, so that is the stuff you'll need to complete that quiz. Those of you in the classroom at the end of class, if you want a hard copy, let me know when I'll get you a hard copy. Talk about relationships between lines. The most common relationship between two lines, something like this, is called oblique. Means there's just nothing special about them. Now in 2 dimensions, oblique lines always intersect. Talked about it before, though in 3 dimensions, just because they're not parallel doesn't mean they have to intersect. I said the word, we should discuss it here, parallel. Mentioned parallel before. In 2 dimensions, it's just saying 2 lines that never intersect is adequate. But in 3 dimensions, remember the definition is always the same distance apart. And then, of course, we have 2 lines that intersect like this. Angle, that's called and the key there is if they intersect at 1 right angle, they intersect at 4 right angles. Because of those things we've gone over before. This angle and this angle are supplements because they combine to form a line. Well, the supplement of 90 degrees is degrees. This angle and this angle are vertical angles. They have to be the same. They have to both be 90 degrees. So with the same logic, you can find that 4th one is 90 degrees as well. So if one of the 4 angles forms a right angle, they all have to be. Of course, we have transversals cutting across lines. And we said if I give you that this angle here is 70, well, let's keep it simple. Let's just call it 70. What's this angle here have to be? 110 degrees. Good. How about this one? This one. And how about this one? One. One. And then this one. Pretty boring, huh? If a set of parallel lines is cut by a transversal, even though there are 8 angles formed, there's only 2 unique angles. So if you know one of the angles, all the others are either equal to it or supplements. We're going to go to the next step and talk about triangles. So we've talked about angles. Triangles can be classified in 2 different ways. Classified with their angles or their sides. Classifying with their angles, this triangle would be called, because the largest angle of that triangle is still an acute angle. So we classify using angles, classify based on the largest angle. That one's acute, this one is. And of course, this one is called the right triangle. If one of the angles is a right angle, that has to be the largest angle, because we know that the angle sum of a triangle is what? 180 degrees. All three angles of a triangle have to add up to 180. I know this angle here is 36 degrees. That is 84 degrees. I can find this one here pretty simple. 180 minus 84 is 96. 36 gives us 60. They have to add up to 180. By that logic, if right angle is 90 degrees, 180 minus 90 only leaves us with 90 degrees. You can't have any other angles that are bigger than. Classified by the sides, we'll start out with the most special. Those little hash marks indicate that those two sides are all equal. What is that called? Lateral. Equal meaning equal, lateral meaning side. Very popular one looks like this. Two sides are equal. One is different. What's that called? Isosceles triangles are everywhere. It's the basis of construction. Most triangles in construction are isosceles triangles. Most wedges are isosceles triangles. V-blocks are isosceles triangles. Properties of the isosceles triangles are going to be very useful in most of our trig that we're going to do. And then, of course, we're going to have a triangle like this. So the different hash marks on each side indicate that all the sides are different lengths. Referred to as scalene. Now, most triangles are referred to as a combination of the two. This would be called isosceles right triangle. Right triangle, but it also has two equal sides. We might have something like this. This would be called obtuse. And of course, that would be this one, which would be called obtuse. Now, if it's a scalene triangle, we don't say scalene. It's just assumed if we don't have any other name with it, that we don't have, that it is scalene, that there's nothing special about it. So it really ends up being mostly the isosceles. It's used with the different angle measurement, angle names. Equilateral, of course, cannot be used with the other angle names because the equilateral triangle must be acute, right? Like all those sides, all those angles are the same. In a triangle, angle to side relationship. In this triangle here, I'll call this A, B, C. That means this side over here would be side AB, side BC, and this is AC or CA, however you want to name it. If I change this angle, make it bigger or smaller, which side does it affect the most? The opposite side that it affects, right? If I kept these two side lengths the same, if I make that angle bigger or smaller, it's that opposite side that's going to get bigger or smaller with the angle. That is called the opposite side. In a triangle, the largest side opposite the largest angle. And vice versa. The largest angle is opposite the largest side. And of course, if that's true, then the smallest side must be the smallest angle is also opposite the smallest side. So in an equilateral triangle, what do we know about the three angles? Same. Yes, they're all the same. And I know that those angles add up to 180, which means each of those angles in an isosceles triangle because of all this. I know that's an isosceles triangle, and if I know that this is a 32-degree angle, I can find these two angles. Because first of all, I know those two angles must be the same because they're opposite sides that are equal. If their opposite sides are equal, those angles have to be equal. So I can just do 180 minus 32 is 148. Divide that by 2 to get 74 degrees. Angles, 74 degrees. Now there are some kind of weird, that's really the basis of what we need to know through. There are some weird things out there that I want to show you, some weird relationships that you run into in machining. They're really kind of weird. Let's just construct an angle here. Let's call that 32 degrees again. What I'm going to do is I'm going to construct angles, or construct lines, I would say, that are parallel to the sides of this angle. If I construct this line parallel to that side, let's do this. I'll call this A, B, and C. That's angle ABC. We always put the vertex in the middle of the letters. This new side I drew is parallel to side AB. If I draw the other side of that angle parallel to side BC, what do I know about the resulting angle? What's going to be the size of the resulting angle? Draw it right here. This angle has to be how big? What if I drew it right here? What does this angle have? Minus 32 or 148. Because if you think about it, if I continue down in this direction, this angle would still have to be 32, right? That has to be the supplement. So if I have an angle that I know the size of, there's another angle somewhere on the part, but both sides of that angle are parallel to the sides of the original angle, it either has to be the same angle or the supplement of that angle. In machining, you run into a lot of parallel surfaces. It'll save you a lot of time calculating angles. Similar. Say this angle here is 36 degrees. And once again, I'll label it sides angle ABC. This time I'm going to construct sides perpendicular to this original sides. I might put one right here, the right angle there. If I construct the other side of that to be perpendicular to this side, side BC, What do I know about the resulting angles? If I do it right here. Now this side is 90, this angle's 90, this is 36. This angle here, because that's a four-sided figure, and we don't necessarily know this yet, but in a four-sided figure, the angle sum is 360. If I subtract 90 and 90, I'm left with 180, right? That means the 36 and whatever's left over have to be supplements again. I know what you meant. 144 degrees. Are there any other possible angles I could form? Well, sure there is. I could draw perpendicular right here. It doesn't necessarily touch this line, but if I extended it, it would be perpendicular over it. This angle has to be. This one's 144. This would have to be 6. So another angle that has its sides perpendicular to both sides of a known angle has that same relationship. Either the resulting angle is the same or it's the supplement. If I have a triangle, and let's say I know this angle here is 35 degrees. Call this B. Figure out the other one, but we don't need to right now. If I draw a side parallel to one side of the triangle, that blue side is parallel to this other blue. What do I know about this angle? This here just becomes a transversal across these two parallel lines. Angles have to be the same. End up with a similar triangle. The triangle is definitely smaller, but the angles are all the same. In order to give you some time to work on the quiz, I'll get you the homework here. First page is out of the old packet. 281, 1 through 12, that's just identifying some angles. There'll be a new packet. Packet, it'll be page 286, 1 through 24. Those are all posted on Blackboard if you want them. Those are in the classroom here, though. I'll give you some copies now so you don't have to print them on your own. I will give you guys the last 15 minutes here to get started on your homework if you like. I'll be here to answer questions. Otherwise,